Welcome back, students. In the last lecture, we have defined what is meant by a signal and what are the dimensionality. What is the dimensionality with respect to the signal? And we said that a signal is a physical quantity or a function, mathematical function, which varies with respect to one or more independent variables, and it carries some information. And the dimensionality of that signal is also related with respect to the number of independent variables it is depending upon. In today's lecture, we shall discuss about some of those basic classifications on signals based upon the nature as well as the characteristics in the time domain. Okay, generally based upon these characteristics in the time domain, the signals may be broadly classified into different types. Okay, and they are one, continuous time signals, continuous UOUS, continuous time signals, and the other one is discrete time signals. Continuous time signals and discrete time signals. A continuous time signal, it may be defined as a mathematical continuous function. This function is defined, okay, generally we represent with respect to the independent variable and the function on that independent. Okay, generally if this function depends upon an independent variable like time, and where it also continuously varies with respect to all the values of time, okay, then we say that it is continuous. Okay, this function is defined continuously in the time domain now, and for continuous time signals, the independent variable that what I am discussing, the independent variable will be time t, and it can be represented with respect to the variation of this f of t with respect to t can be represented something like this. Here we can say that, okay, the shape, let us consider the shape of the signal is something like this. Here we can say that a signal of some continuous amplitude, continuous in the sense it takes any value on the y-axis, okay, or on the x-axis. If at all, if we are defining that independent variables with respect to each and every value, that means each and every value on the x-axis, then I say that it is a continuous variable. Okay, so something like a set of real numbers which defines this x-axis is a continuous variable. Okay, it depends. It now becomes a continuous variable when I represent my time t, which is representing this x-axis with respect to whatever number that you define from minus infinity to plus infinity. That number is present on this x-axis, and with respect to these particular continuous values, if your amplitude also takes a continuum of values generally, okay, where that amplitude is also continuous, then I call, okay, here my main concern is about, since with respect to the time axis, then generally these kind of signals we call them as continuous time signals. Okay, and this signal will have definitely some value at every instant of time. The electrical signals that are derived in proportion with respect to the physical quantities such as temperature, pressure, or sound, etc., they can be actually considered as examples of these kind of signals. The other examples of continuous time signals can be taken as the cosine waves or the sine waves that what we draw generally. Okay, the cosine waves or the sine waves that what we draw, or the triangular signals that what we shape, that what we show. They're generally considered as the examples of these continuous time signals. And the continuous time signals are represented by f of t, where f represents the shape of the signal and t shows the variable of the time. Okay, and based upon this continuous time, and the other one is the discrete time signal. Okay, so let us see what we mean by a discrete time signal. And a discrete time is analogous to this particular continuous time signal. A discrete time signal is generally defined only at certain time instants. Instead of defining with respect to each and every value on this x-axis, now it is defined only with respect to certain numbers, certain values over time. Let us consider, as I said, as a set of real numbers represents a x-axis in the case of continuous time signals. Here, the set of natural numbers or the set of integer values, such as minus infinity to plus infinity, they generally represents this particular time axis. In such a case, this x-axis will take only certain numbers such as 0, 1, 2, 3, 4, so on the positive side, and similarly minus 1, minus 2, minus 3, so on until negative side. Therefore, they are only at certain time instants like 0 and 1. We are not having any information with respect to the time between those two values of 0 and 1, or 1 or 2, or 1, 2 or 3, something like that. Okay, it doesn't have any information. And for discrete time, the amplitude between any two time instants is defined. All I consider 0 and 1, here the amplitude is defined and here the amplitude is defined, and there is nothing defined, the point between these two values. Similarly with respect to this, okay, at only certain instants of time, here amplitudes are defined. In such a case, I call them as discrete time signals. Generally, for discrete time signals, the independent variable which we generally time is represented by n, small n. Small n is the representation that what we take for the independent variable, and this n also represents time, but since it is discrete, I'll show with some another independent variable like n. And for discrete time signals, the amplitudes are once again represented as a function of n, and we write it as f of n. Okay, f of n. This means that to represent a discrete time signal, we shall enclose this particular n, independent variable n, in brackets, and generally now I would like to show you some values. Okay, some values with respect to 0, 1, 2, 3, 4, minus 1, and so on. These are the amplitudes. Okay, and you could see here the amplitude at 0, we generally now write it as f of 0, and the amplitude at write it as f of minus 1. The amplitude at 1, we write it as f of 1. Okay, amplitude at 2, similarly f of 2, f of 3, and f of 4. Okay, that is what I was talking. The representation of the discrete time signal, where we enclose the independent variable n with respect to in brackets actually. And thus we can say that if the signal is represented only at a discrete instance of time, then this is known as a discrete time signal. And also the discrete time signals have also values only at certain instants of time. Okay, let us consider a simple example for this. If we consider any blood pressure readings of any patient after every 1 hour or every half an hour and plot the graph, then the resultant signal will be a discrete time signal, because here we are defining at regular time intervals, that is with respect to some every half an hour or 1 hour. Okay, therefore mathematically a discrete time signal is also written in flower brackets. The amplitudes are represented in flower brackets, where let us consider some example like f of n, where the amplitudes are noted with respect to different values like 1, 2, 3, 4, 5, and so on, and the origin is generally denoted with respect to a arrow mark, something like this. Okay, these all the values they represent with respect to the amplitudes at different values of time, and this arrow mark actually designates that the origin is present here and it represents x of 0. And to write off this x of 0, this value represents x of 1, and this value represents x of 2, and so on. And similarly, To the left of this origin, you see the amplitude at x of at -1, at n is equal to -1, at n is equal to -2, and so on. Okay, and this arrow indicates the value of the x of n at n is equal to 0. Please remind that. Okay, and I would like to say some another classification based upon this continuous time and continuous discrete times. If you observe here, if you observe the both the continuous time signals and discrete time, we have only classified them with respect to this time. Okay, that is with respect to the x-axis, and we haven't talked anything about the y-axis. Okay, here if you clearly observe that y-axis is also taking the continuous continuum of values in both the examples. Continuous in the sense it is represented for every value on the y-axis also. Okay, that means the range or the set of values that are represented with respect to this, it is a set of something like real numbers. It can take any value from -infinity to +infinity as an amplitude for the times that are represented here as well as here also. Okay, I haven't represented any specific value that it is rounded to a specific integer value. It is represented as some f of 1. It can take any integer value also, something like that, any fractional value also, 0.1, 0.2, and so on. Okay, they all represent some amplitudes with respect to some real numbers. In such a case, can I call that the amplitudes in both the cases are continuous in nature? That means this is a signal which is continuous in time as well as continuous in amplitude, and this is a discrete time signal with amplitudes having continuum of values. Therefore, there lies another classification such as analog. Okay, analog signals. We call such signals as analog signals whose amplitude is always continuous. Okay, if the amplitude is continuous, then I can call such signals to be analog signals. This is an example for analog continuous time signal, and this is an example for analog discrete time signal, because in both the cases the amplitude was continuous. Hope you understand. Okay, it's an important classification, and many of the students generally confused with the definition of an analog signal. They consider only this kind of continuous time signals to be analog signals. The discrete time signals are also analog whenever their amplitudes are continuous. So now, and the process of converting a continuous time signal into a discrete time signal is called as sampling. We call the process of converting a continuous time signal into a discrete time signal, we call that it as sampling. And the process of conversion of a continuous amplitude into discrete amplitudes, or rounding of the amplitudes to some nearest value integer values, generally we call such a particular process or such method, we call it as quantization. Okay, quantization. Quantization is the process of rounding of the amplitudes to nearest integer values instead of representing with respect to the real numbers. Whereas sampling, it is a process of converting a continuous time signal into a discrete time signal. Now we have clearly seen what is the difference between a continuous time signal, a discrete time signal, and what is an analog signal. Hope you understood this. And similarly, there is another classification like digital signal. And the digital signal is generally a signal whose amplitude as well as time both are discrete in nature. Okay, you might have heard about these digital signals. Digital signals are those signals whose amplitude is continuous as well as amplitude is discrete as well as time is also discrete. Okay, let us consider. Let me show some example for a discrete time signal. Let us consider a discrete time signal or a which is represented only with respect to specific values, and the amplitude is also now specifically defined only at some discrete instance and have some discrete values, something like this. Okay, they are all represented with respect to some integer values only. Okay, here the amplitudes are not defined between these ranges. Okay, they are defined only at these points. Okay, and such signals where you could see that the amplitudes are defined only at some specific values, and the x-axis, the time axis, is also discrete in nature. Okay, both the y-axis as well as the x-axis, both are discrete in nature, and this is an example of a digital signal. Okay, so now we have clearly studied what is the difference between a continuous time signal, a discrete time signal, and what is meant by an analog signal, what is meant by a digital signal, and what is the process of sampling and quantizations.